Okay, so this brings us to our fifth lecture, and I've entitled it The Business Cycle and the Fourier Transform. So we're taking a really big step here. We've been talking about this Laplace transform, and we've talked about it in terms of a discount rate and present values. And I just had a great discussion with one of the students here. Anyway, what became clear is that this concept of the real part of the Laplace transformation is really sunk in. It's kind of easy to look at. To look at any type of, I think I got to. So if I take any type of what we call a cash flow here, and just be careful, I'm using here this notation F for force. I could have used the notation tau for a torque, all right? But what I consider here is a signal, right? So usually I don't just plug in some kind of energy or something here. We never do that in engineering either, okay? And there are two different types of definitions for a cash flow. One is the thing that's actually happening as an accountant uses it in the cash flow statement. But the other is the way in which business people use it. That is, they look at potential cash flows from investments. Now, none of these are realized in any way. They're all imaginary, and they're all looking at what-if scenarios, okay? And that is the idea behind the Fourier and the Laplace transform, that this is time, as the notation suggests, and we're looking from the now, and we're looking in the future. All right, and this is a signal. So this could be a regular force, and then the units of this will be something like that. All right, and only in the case when it's a cash flow, that is a torque, do you just get that the units are. And so it's the rotational analog that fits the best. Now, what we've been doing up to now is looking at discounting, where instead of this I omega, we just put a real variable. Let me call it sigma here. I was calling it S, but S I'm going to now use as a complex variable. And then it's very intuitive what this thing says. You just take this cash flow here, and I mean a torque, right? And you look at any moment of the future, and you just discount it with this as the discount factor. And you add them all up, because obviously this is a signal that's going from now to infinity, and then you're done, and you get the value of this project. Now, that doesn't mean that you actually paid this money, you just valued it, right? Doesn't really mean that you got how much of this you're going to buy. You may buy some shares into a company or this, but you're just valuing the shares, and you don't know how many shares you're going to buy. So this is quite separate from the flow, all right? I'm harking a little bit back over the discussion I just had with Quinton, okay? All right, so that you have to understand. Now, we found that it was very intuitive, and then we did our usual analysis, and we looked at the poles, and still we have this to be equal to sigma is a real number. Okay, and we found these poles very convenient. Now, why were they so convenient? Can anybody tell me that? Wouter, do you know? What's so great about finding the pole of this thing? No, from an economic perspective, you know. Why are these poles, why were they so interesting, you know? So this is good to kind of bear in mind again. You know it, but you've got to kind of hammer this home to you.
The normal getting system, the poles are the frequencies where the system explodes.
Yes.
So here I would guess it's the discount factors where the value explodes.
Yes. So what would that be over perpetuity? So perpetuity is a constant payment, right, over time. Huh? So here is your cash flow. Here's time. Where's the pole located here? You know it.
That's zero.
No, not at infinity, because infinity would mean you plug in infinity here, you will like really discount it down, and the whole thing is worth zero, right? So that's precisely not the case. It's at zero. And what is that really saying? It's saying if you just take a cash flow and the future is just as great for you as the present, you just add them all up from now to infinity, how much you're going to get? Infinity, of course, right? So what is that doing? That's saying when the discount rate, when the pole is at infinity, that means that only if you doesn't discount at all, you're gonna, this thing will explode. That means that you've got a perpetuity, right? It can't be this thing. It can't be going down exponentially, because if you discount that with zero, you're just going to get a nice finite number, which is the integral of the exponential, right? Huh? But now suppose you have this increasing payments, so they index it with inflation and you get more and more and more, right? Huh? Then what will be where will be the pole? Yeah, but where would it be? Huh? I don't think it's positive, because this thing is already positive. Now you put in a positive pole, then, but I don't know what it means really. Where would it be? Well, what you would do is you try to figure out when this thing blows up, right? So when does this thing just blow up? Suppose I'm like discounting like a maniac like that, right? So I'm discounting much faster than I'm growing. Then this thing will be okay, right? It will converge, right? So when it will just start diverging? Well, when I'm discounting exactly at the same rate as you're inflating me away, right? You're growing my cash flow, right? So I find that the pole is exactly at the location okay, what the growth is here, all right? Okay? So the pole is really good at picking out what I'm dealing with, right? So I just go and tweak this thing, this discount rate, and I find it converges, and then it diverges, and I know where I am. I got the best fit, as it were. It's not really the fit, because you got this minus sign, so you got to knock it down. But since that minus sign is already provided, I know that whatever this sigma is going to be exactly equal to my growth rate, because that's how much I have to knock it down, right? That's what's so great about the pole. Because when you know it diverges, you know exactly, okay, this is what I have. This is the signal I have, right? Huh? That's also the idea behind the Fourier transform. You've got something else going, and it's going up and down, and that thing you'll never be able to get that to diverge, right? Huh? So suppose you have this signal, right? What's the pole here? If you just let this be a real number. Oh, no, it's a real number, right? So I omega is just sigma, huh? So I can only discount this. Is there a pole? There is no pole. Not in the left half plane, right? Well, what if you just take no discounting? You're just adding up the signal. What are you going to get? You're going to have some positive payments, then some equal negative payments. This thing is just going to go boo, 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 right? Huh? It's definitely not going to, huh? Now you kind of go like this. Now that's not going to improve the situation. Then you go like this. Sure, this gets bigger, but then the negative afterwards gets bigger too, right? So the thing starts flopping up and down, right, like crazy between two numbers, all right? But is it going to converge to one point at infinity? Definitely not, right? So there is no pole here, okay? This is the problem with just using a real number. You can only look at signals that look, only pick up the trend. Huh? So when you just have this sigma, so S is equal to sigma, and there is no frequency, then you can only pick out a trend, right? Exponential growth or exponential shrinkage. Huh? All right? And then we'll see also you can put You can have multiple trends. So it could be that you're doing hyperbolic discounting. You go first a little slow and then a little faster, and you'll get two poles and they'll conjugate. And we'll talk a little bit about that. All right? Further, we already did that in the last lecture. Okay? But this is good to keep in your mind, right? So what the real part of the Laplace transform does, normally we think of this as a complex number, as this one just picks up the trend, right? So if you have poles on the real axis, you're just going to get out some trend line, all right? And if you don't have a trend, you just have something oscillating, you're just going to have be mighty hard to find a pole just on the real axis, okay? So you can discount all you want, but you're not going to pick out the cyclic nature of it, all right? So suppose you're an economic agent, some investor, and you're just doing buy and hold, then you just want to look at the real part of the Laplace transform. I mean, just look, I'm going to buy now, and I want to just pick up the trend, how this thing is moving. I don't care about all these frequencies. You know, just average them all out, just discount them away, so these frequencies in the future don't matter at all. Huh? So, boom. Huh? No need for anything else. But now you're a trader. You want to turn around. You want to buy high? No, you don't. You want to buy low and you want to sell high, right? So you certainly want to pick out what that frequency is. Okay, so we need to expand this notion of poles so we can find out where these frequencies are sitting and simultaneously figure out where the trends are sitting. Because we may be trading and buy and holding at the same time. You know, we may be long and we may not be neutral, right? We may be, we maybe have a long position that we're riding and we have some other position that we're trading, okay? Right? Or a regular business, maybe you're just buying and selling some products, but they may also have their facilities, which, maybe are growing in value in time and they can sell later, when the guy retires who has the business, he just wants to sell the whole thing. So he wants that thing to keep growing, but at the same time, he wants to pick out some frequency at which he can sell the products that he's making. All right? So what we're doing here is trying to complete the picture of what it means to figure out what the value of a business is. The value of business is not just the stuff that you sell at the end, but it's also all the earnings you get in the meantime, all right? But in order to get any earnings, you got to buy low and sell high. If you're just buying high and then selling low, this is not going to work either. Your buildings can be worth all you want, but you're still going to go bankrupt, okay? So when we value a business or we value a portfolio and it's traded, so then we have to take care. We have to look at both these factors in the Laplace transform. All right. Now suppose you guys all paid attention last semester and we did all this Newtonian mechanics. So let me suppose that I have a system, I don't know, like this. Here's a mass and here's a damper. So we just have a little bit of a demand here and some transaction costs, right? Now, can this represent somebody in a cyclical kind of business, right? No, right? I see a lot of no nods. You can only have a trend here, and the trend is down, right? That's clear. You take some stuff, you have your whatever, your demand or your supply, you just kind of, through your transaction costs, you're just killing yourself, right? You wouldn't do it, but it's a valid way of describing some possible behavior, right? And the situation doesn't get much better if I have some storage, right? And I have some cost of carry, and then maybe I have this thing is out of equilibrium, bring it here, just going to go, there's not going to be any frequency, right? These are all first order systems. So first order system, I only have a trend. You know that, right? From your engineering, and now you see that. I mean, this just makes sense. A first order economic system, you don't have to mess with all this I omega stuff, all right? So in order to get a second order system, in order to get these reversals, we need to add, at least a spring here or a mass here, right? We need to go to second order system. Okay? Now, if you have a second order system, how many poles do you have? You guys know that. How many? 2. Maybe 2 poles. Huh? So we already met situations last week with 2 poles where we had these hyperbolic systems and they had 2 exponentials, 2 trands. Okay? Actually, there's only 1 trend, and there are 2 deviations from that 1 trend. One going a little bit up in the short time, and the other going below the overall trend. All right? So what you'll see, you still have only 1 trend, but you get 2 conjugate poles, you're now measuring how the spread around that is. Okay? And that measures a person who, and a lot of people are like that, even on the stock market or in business, where they discount future rewards not evenly, but say, well, the immediate future is more important than the late future. A lot of liquidity problems are like that. People now need something. They need to sell this. They need to cover a short. They need the stuff now. They're willing to pay a lot more for it now than later, right? And they're certainly not going to exponentially discount it. So in the economic literature, you'll read a lot about how this is inconsistent and blah, 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 but it is not, all right? And the problem you can see, you have some storage here, you have some demand, and it better be that when you want to demand something, you've got enough in storage. Your storage is not pulling at you going like, this is super inconvenient. I don't have anything anymore, right? Huh? So, okay. All right. So you see, for any interesting business, it's going to see some fluctuations around this trend, okay? So for second order systems, we see fluctuations around the normal exponential decay implied by an element, energy storage element, and a damper, all right? You can also take one energy storage element with no damper, and then you're just going to get a perpetuity, The thing just won't damp. But you still only have a first order system, all right? Now, last week, I kind of I finessed the issue a little bit just to get on with the uncertainty, because I wanted to show you that there's 2 poles and that the one in the northern hemisphere, one in the southern, and they're equally distributed. And this time, I want to do the opposite and really drive the point home in the real time, the overdamped thing, and then proceed to the underdamped thing. All right? But let me, after now this big introduction about the need for a second order system, let me move immediately on for why do we need this number I, right? Okay. This is pretty funky, right? Because we need this I thing here, right? Now this is the I of imaginary, so we imagine this number to be, at least I don't think it's imaginary, but that's the name that's given to it, right? And it's a number so that when you square it, you get -1. Okay, now that's how they define it. And then you can say, well, good luck to you in sorting out what this has to do with economics. Okay? Can you please come back tomorrow and explain to me how this figures this number I with this definition? Huh? Now makes this all very intuitive. Right? No. Right? Because here you run into all kinds of problems, because you will see quickly that if you evaluate this integral, this will be a complex number too, right? Huh? Does everybody see that? Huh? Yeah, because this is cosine omega theta plus I sine. So you're going to have some imaginary part floating around there, unless omega is 0, which is certainly not so interesting because the thing is not moving, right? So what is that meaning for imaginary values? Yeah, okay, and it's just no problem. Just say I squared is -1. Right? No. Huh? Huh? So this is a big hurdle. Right? It is a big hurdle in engineering too, but the usual approach that gets taken to this is to, not worry yourself too much about the conceptual hurdle, just show that it all works, and that the math works, and at the end you do an inverse or you throw away the imaginary part and you say, okay, done. It's a convenient way of dealing with it, and it's kind of magic how it works, okay? Now that won't help us in economic engineering. We got to kind of unravel the magic. So the way I want to start, then start this whole lecture is before diving into conjugacy of poles is first kind of become a little bit more comfortable with this number I. So I have one slide on that. So if you will, for some of you this may be trivial, but I feel that it's good to kind of put everything in one slide, all right? So let me see that I can get this. So I want to give a little primer on complex numbers and how this number I shows up and what its meaning will be in economics. So here you go. There's a slide on complex numbers. Now I wrote kind of this thing as a sort of teaser on top here because this is considered like this magical equation in math, okay? And why? Because it combines 1, 2, 3, 4. I don't know why I put the minus sign here. Let's just leave that a plus, okay? It combines 4, it's true anyway. Huh? It's the same, but...
the poem is like,
What?
poem is like...
Yeah. Yeah. So it's famous because it combines 4 funky things that the Greeks didn't know about. The Greeks are the ones who supposedly invented the kind of mathematics that we use in the Western world. The number E, the magical number I, the other magical number pi, you know, and then the negative numbers, right? Okay, in one equation. Now, this equation is kind of, you look at it and you think like, how the heck is that true, right? And then guys will go take logs and then certainly figure out that it's true. But what I kind of want to do here is make this self-evident, okay? That from now on, when you look at an equation like this, you can just see, of course, one. And what else? You guys know anything about complex numbers or not? All right? So that's what I want to achieve with this slide, okay? Now, this is just an interesting history because it has everything to do with the way numbers developed, you know? So I kind of went back, it was a while ago, and looked at the history of numbers, and it appears that the simplest way in which numbers are used is for counting, okay? So you just want to say, I have 5 bushels of wheat, so you're a Sumerian trader, you have 5 bushels of wheat, and then you come up with this number 5. It was actually the Arabs who came up with this number system. The Romans would write something like this, you know, a V, it doesn't matter. So you would just count 5, so 1, 2, 3, 4, and then 5, and then you say, okay, I got 5 bushels of wheat, and you can have 6 bushels and 7 bushels, you know. And if you do that, then there's really no need for a number 0, right? You can't even write this really down with this hash mark system, right? So you're a Sumerian guy with your tablet, you just have nothing. So, and why? I mean, why talk about nothing, right? That's only people in academics who do that. You know, you're a trader, all right? And then I ask you, what's the need for negative numbers? Now, nobody had seen a negative bushel of wheat, so, and neither have we seen that now, right? So that's not needed either. And certainly not imaginary numbers, because there's imaginary bushels of wheat, and those are obviously not to be traded, right? Only the government will give you those, but these were real traders. Okay? So you see, if you're just counting, and you're counting money, right, and counting goods, there's no need for 0 or negative numbers. All right? Now, the first big step was taken by the Greeks that started using numbers not just for counting things, but for geometry. So they also started counting, right? So instead of just counting bushels of wheat, you start counting how many times you can fit a foot or a thumb, which is an inch, right? Or something, a nose length, I don't care, right? or your arm, an L, we say in Dutch. Huh? You can fit, how many times you can fit a meter rod in somewhere, right? Huh? And then you just start off wherever you want, and then you start fitting it in, okay? And then you can just start counting how many times you fit it in. So you can say, I make a meter rod, I counted 5 times, I put them, concatenate them together, so this is 5 meters, right? All right, so you're doing okay. And then you can say, now I have a table, and here's the 5 meters, and now there's a little bit left, a half. So what do I need to do to measure that? Well, I take that meter rod and I break it in 2, right? So what did I do? I broke 1 meter rod in 2, right? So this is breaking, and then I say, well, I can fit a half one, so then I can break that one in 2, then I take a quarter, right? And you can even say, ja, Kunjan.
Je microfoon is uitgevallen, maar hoor je nu wel over de algemene.
Ja. Nu wel. So you can take a quarter, you can get tired of that, you can say, you know what, I'll just make notches of 12 notches on my meter rod so I can break it in by 12 because I can divide by 4, I can divide by 3, I can divide by 6, I can do all this stuff. That's why I choose 12 for a dozen. That's why there's 12 inches in a foot, because it's easy to break up that meter rod, right? And then you do that, you quickly figure out that you got more numbers, like namely the rational numbers, right? Okay. So that's fine. There's the Greeks that sorted that out. By breaking, you can find all rational numbers. Just count the number of times you break, okay? All right, okay? But still no need for 0 or irrational numbers, right? Okay? Just bear with me, because this is how we're going to come to complex numbers. Then you can say, well, all right, so I'm cool. So I have this. I measure it by breaking my meter rod. I do that. But now I'm interested in what this length is here, right? Now, and you figure out that there is no way to do that with rational numbers by breaking the meter rod. This is a serious problem. Huh? And the problem is because what you're really doing is you're summing these squares and setting it equal to this square, okay? So you're squaring and you're looking at area, not to length anymore, okay? So you're measuring area, so now you have to take square roots, and then all of a sudden you can't take square roots of everything if you insist on calling that a length, okay? So then you need to get real numbers, huh? All right? So I'm going to go a little bit, there's a lot to say about real numbers and why you get there. Well, they kind of never got there, but they knew they must have been out there, okay? And this is the situation how it was until like in the end of the Middle Ages, and maybe the Arabs did some of this, and it was important during the Crusades in Europe, that they figured out that, okay, if I'm measuring and I start at this point, let's call this point, then I can measure 1, 2, 3, 4 and a half. But now I measure the other way. I just, instead of going this way, I want to go that way because that's the depth and this is the height or something. Then I can measure this one, this one, this one, and this one, right? So you quickly find out that what you're doing here, placing those meter rods there, is actually the same. You just turn around and did that, all right? And why did they do that? Because they were geometers, and for imaginary numbers, the big guy was Gauss, and he was employed as a geometer by the court of the Count of Duke of Weimar or something, right? Because these princes, they needed to know how much land they had and what these distances were, etc., because they would fight over this. Okay, this was serious business, of course, because that was the means of production. So then they'll say, well, here's the castle, and then if you go this direction, it's so much, and from that point, it's so much. So then you can see that you can't call this distance 1 anymore because you already got a distance 1. So you got to somehow say that it's 1, but in a, reflected over where your castle is standing here. So to do that, they put this minus sign in front of it, okay? So if you have 5, you can just say, well, if I went the other way, I'll just say it's minus 5. And I'll just arrange them on this axis, okay? Now, once you've done that, you'll realize that you need, this pivot point is quite important because that's your reference point, right? So you can call this A and P if you're Dutch, right? And you're measuring depth. You just got to say what that is, right? So, and if I did a movement and I came back here, I did nothing really, right? I'm just at my pivot point. So I call that 0. You see, I already put it in here, 0. So only if I have 2 sides do I realize I need this number 0. So now we got 0 and we got negative numbers, right? Okay? Everybody cool? This is how it goes. And then you can say, well, I can now do something that's called algebra. That's also something they got from the Arabs because al is like Alhambra or something is the Arab article, and then this means something like counting or, it means all these words that sound like al are Arab, like alcohol, right? It means the something. So they got this, and now we say we want to do algebra. So instead of saying, hey, I put a minus sign in front of it because I'm going the other way, what I want to do is to say I have some number, x, and I rotate it 180 degrees, so I multiply that by minus 1, right? And this act of multiplying, a little confusing with x's and multiplication symbols, so I'm going to use this convolution symbol here. Yeah, well, if it's not confusing when you're typesetting in LaTeX, then, so this means multiply, right? Actually, what I want to do, this is much better, I made a little composition, function composition. This is what you would do in group theory. 1 times, minus 1 times x. It means take wherever you are, x, go floop, and there you are. Actually, you don't have to do floop, you just imagine a little mirror here and you just look the other way. All right? So this is a nice thing because instead of saying, well, I'm rotating 180 degrees, I say, I'm just multiplying by minus 1. Right? So I can do any type of complicated math to do this, multiply the whole shebang by minus 1, and boom, I'm on the other side, or I can integrate it. So I can like model my concatenations with plus, right? So that's concatenating, putting the meters together, and I can do all this flipping by multiplying, right? That's the idea, right? And when you are adding and multiplying, you have what we call an algebra, right? Otherwise, you just have a vector space. All right? All right. So simple, right? Took thousands of years, right? It's like to do this. It's weird, huh? And if you look at it now, you go like, okay, whatever, guys, huh? But thousands of years. And then you see a lot of people do very magical about 0 and who invented it. I mean, well, what's the point? It's just the point from when you start going and it's an agreement, huh? Okay? All right? Now you say to yourself, where did these imaginary come from? And this is really where Gauss, it's called the Argand plane. I'm not quite sure, maybe. There is some rule in mathematics, I've been told, that these things are always named after the person who didn't invent it. So haven't you heard of that? Huh? Yeah. So it's called the Argand plane, I think, right? Huh? But doesn't really matter. A point is to see that, listen, if you're prospecting, we have to do area. You can only do area if you have at least 2 dimensions, right? So this lord that you're employed with, he doesn't have a length that he needs to travel. He needs to also know what the width is simultaneously of the land he has, all right? So we're really, when we're doing geometry, and geometry just means how to measure earth, right? Huh? So geo means earth, and this just means measure, right? Huh? We need to deal, we can't just have these real numbers. It's just not enough, all right? And they didn't have vectors yet. Those were not invented. Those were, I think, invented by Hamilton and then worked out by Gibbs and Maxwell. So 19th century, right? Huh? So they said, all right, this is 1, this is -1. So let's just use a Roman 1 for this direction, right? Okay. So I get that if I do a 90-degree turn, and this will be like 180, right? Huh? And I'll call this, obviously, if I go from here 180 degrees, I multiply by -1, right? So I don't need a new name for this. I can just call this -I then, right? So suppress for the moment this idea that this stands for imaginary, but think of this as a Roman 1, huh? Okay, Roman unity. Okay? Then we want to do the same trick. Here we multiply 1 by -1 to get -1, or 5 by -1 to get -5. Here we want to multiply 1 by I to get I, right? Okay? And that is a 90-degree angle, right? Huh? So I take 1, I multiply by this number I, and I should get this distance, right? Okay? That's just what my geometry is telling me. Then I know that when I'm here and I go another 90 degrees, I should end up at -1. So I want to do 1 times I times another 90-degree rotation. That should be -1, right? Huh? So what does that imply? I squared is -1, right? Simple. This is saying that if you rotate twice 90 degrees, you're going to end up at at 100 degrees rotation. Okay? You follow that? So simple, right? So this is magic formula number 1. That's just simple. All right? So you rotate over 0 degrees, I'll multiply by 1. 180 degrees, I'll multiply by -1. At 90 degrees, I'll multiply by I, right? Huh? So I immediately know I squared is -1. What about I to the 3rd? What is that? What?
I.
Minus I, of course, right? I -1 minus I, right? Huh? And why is that minus I? Well, it's just a reflection of I, right? What is I to the 4th? Yeah. Simple, right? Huh? Okay. Now you can ask yourself, what is I to the power of a half or something like that? So obviously that's going to be somewhere, now. If you multiply that by another I to a minus a half, what do you get? Then you get I, right? Huh? These exponents just add. Huh? So you see that it's something that you multiply by yourself, so this must be a foot. Right? Okay? Now you can work this business out. And we'll do that someday, but really, this is what you get. Okay? Now you rotate it over some angle, and then you guys just, it's a little bit of a definition thing, but you get here cosine theta, and here you'll see I sine theta. Huh? All right? So, all right. Now that's Euler's famous formula. I looked at what Euler's comment was, and he was just he thought it was totally magic, and given his brilliance, I failed to see that. You know, I think Gauss came a little bit later, and he saw that this is just saying something about a rotation. I don't think Euler saw that. Huh? Okay. Now you guys all know that this is e to the I theta, right? Huh? So, huh? So now you know what this is, huh? In your Fourier transform, you're just rotating, huh? Just a rotation. So now why is this thing trivial here? Why is e to the I pi? Huh? Why is that -1? Why is that trivial? Yeah, so what is pi? Is 180-degree rotation, right? I once was in a bar, believe it or not, and some guy was saying, oh yeah, and he could prove it, and he had a new proof. And he showed up with like 5 pages of proof, and it was shorter than the proof he'd found somewhere else. And he dared me to prove it to him. And I gave this little thing, and I don't know, he looked like totally deflated, right? It ruined his day. It wasn't deep, you know? It was just a rotation of 180 degrees, okay? So this is just a little bit of a primer on numbers and where these complex numbers come from. But the thing to keep in mind is as soon as you talk complex numbers, you're talking about a circle, okay? That's why they use polar forms. That's why in the Fourier transform, we'll see all you do is wrap the function around the circle and see how well it fits the circle, okay? That's the way to look at it, huh? So you have your test circles, and you're kind of testing it with your other functions that you also look at a circle, and you see when they're in sync. You know, the 2 wheels are in sync, you know, as gears. And when you find that they're in sync, you know, but, you know, you got a pull. Huh? All right? Okay. Any questions about this for now? So it's a long preamble, but it's worth our while. Otherwise, it all remains abstract. So this is, you guys knew all this already? Huh? Okay. This is how they teach it? I did it last year. Well, it's good to, you know, once in a while I ask somebody to do that, and they still make a mistake. So it's good to refresh yourself. All right? Okay. So let's keep going. So now, okay, so this is a little better, and now we can look at this thing, right? So I looked at positive ones. This is just turning the negative direction. But remember, in the real case, we had positive growth, and we had to do negative growth to beat it down, right? And that's the thing we're doing here. We have some kind of positive frequency, and we need a negative frequency to go and beat it down to see when it just diverges the integral, right? So there you see the I sign. Here you see that I'm just, you know, running around the circle because this was my angle theta, right? So now you can look at this formula and go like, all right, you know, of course he taught that last semester, but this is still helpful to stare at this thing, right? Okay. All right. So now put that out of your mind, because our next problem, so we have the right way to look at this now, but our next problem is that we got 2 poles, and the trend is only 1 pole on the real axis. So we have to do a little bit of time now talking about conjugacy, all right? One variables show to, you know, turn out to be conjugate, okay? There's a general notion of conjugacy, all right? So if you have something like a number a plus b, then the conjugate will be a minus b. And why is that cool? That if you multiply these, then you get a squared minus b squared, because the cross terms vanish, right? That's the thing about conjugacy, algebraically, right? So you see, algebraically, these guys were always looking at area. So here you see, this is the area of one square, and you subtract the area of another square. So this is what they called completing the square. And this is just where a lot of that mathematics was focused on. That's how they got the number pi too, because they wanted to know the area of a circle, right? And the number e was the area under a hyperbola, right? It's not quite the area. And if the area is 1, then the extension is e, you know? That's where these numbers come from, right? So it's all these area calculations, and you see that conjugacy is just a really nice feature to have, because you can see that it's just a simple difference between two areas, right? That's how you prove Pythagoras' theorem too, right? You do a squared plus b squared is c squared, right? Huh? You know. So these things, second order systems, they imply the structure of conjugacy. All right, so I have a trend plus 2 conjugate poles. Huh? That trend, and then around the trend are 2 conjugate poles. So what I want to do first is look at the real case. We'll find it's not really real, actually. It's also 2-dimensional, right? And maybe this is another point I'd like to make. You'll see complex numbers only make sense for area 2-dimensional, right? But all this other stuff we kind of did only in 1 dimension. We just had time running along, right? And then just 1 discount rate. So where's the other dimension, right? Huh? Where's the other dimension? Now, for first order systems, there are none, but for second order systems, they're 2-dimensional. So you need complex numbers. What kind of shape? Because you need another axis for the second dimension, right? And then you get these notions of conjugacy. So second order systems, their natural kind of state space is 2-dimensional, all right? That's what it means to be. So complex numbers of some form or other are going to play a role, even when all the poles are real, all right? Okay. So now we're going to attack this problem. And what I want to do is just go back again to our examples that we saw of second order systems. This will be the last slide I want to do for before the break. All right? And quickly go through there why we get 2 poles. So second order systems, you can see that the value, the present value, has got a square, right? This is how you recognize that, right? So this is weird because a regular perpetuity we know is 1 over s. Now what is 1 over s squared, right? What does that correspond to economically? And the answer is, well, you're kind of squaring the perpetuity. What does it mean to square the perpetuity? Well, not to do 1 squared, the coupon squared. It's just 1, right? So what you're saying then economically is that instead of getting your coupon $1 every moment, every compounding point, right, you get another perpetuity. All right? Okay? That's what a ramp really is saying, right? So every time you're not going, oh, like this, you get another one and another one, right? Huh? So here, the second order effect comes from the fact that you got this ramp. Every time you push in a bigger perpetuity forever, right? Because every time you'll see, you can build this up with all these little ramps, okay? And this shows up as the square here. Okay? So if you just have a perpetuity, that's not going to work. You need a perpetuity of perpetuities. So all the time you're getting a new perpetuity. They have these things. But let's not discuss that. You all know, what's the pole here? Where is the pole? Well, it's 0, of course. So here's the Riemann sphere. Boom, it's 0. But I got 2, right? So this is the way we draw those. We just draw them like that. Where? We got 2 there, right? All right? Okay. Now, I want to look at some variations on this theme. So here is something that is an exponential approach, right? So that thing will do something like this, right? So you can have some trader or some storage, and you give it a, you put something in there, and because of the damping, this is how it goes. Or, you can easily imagine economic systems that do this. All right? So you see, this is the problem, right? You got one here, 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 right? Until you're at equilibrium. Okay? And then if you work it out, you'll see this is the Laplace transform. That's elementary, right? Okay. So where are the poles? Well, you see one of them remains at 0. That's this one, right? And this one moves over. And then when you look at the projection on the S-plane, you'll find it here. But in the Riemann sphere, you'll see that this thing goes from here, it just kind of rotates over to end up over there. All right? Okay. All right, cool. So let's go and make it ourselves a little. This is another one we were looking at, remember? This is the cinch. And we looked at the sign, I think. And then there's a plus sign here. If you look at the cinch, there'll be a minus sign. Here. And then you'll see, let me talk a little bit later about what this represents. Let me first tell you what you get. You'll see that both poles move symmetrically. One is moving over here. This is the omega there. And then, no, that's this one, right? And then here's a positive one, right? Moving over here. So you see them fanning out like that on the Riemann sphere, right? And then you can draw a little bar here, and you can see there's something cool about this. It's like they're conjugate, right? And you see, this is this idea of conjugates, you see, that I was talking about a little bit earlier, right? So you can just look at S squared minus omega squared. On the Riemann sphere, it's just all elementary, right? Okay. Now, you think to yourself, now what economic system goes with that cinch? I mean, give me a break. I don't even know what this is. I remember learning this at some algebra class. I mean, what is this guy talking about? But look at the definition of the cinch. You take two exponentials, okay? And here, you take it, just a positive one, so this is some growth, right? This is a negative one, so this thing contracts, right? Okay? If you have the cosh, there's just a plus sign here. So you can either plus or minus, okay? Now, what could that be? Well, suppose you have a portfolio, and some of it is growing, and half of it is growing. I'll put that half in front of there at this rate, and the other half is contracting at that other rate. That's you borrowed it, right? Okay, at that rate. Now, that will be the flow, the cash flow then, right? You got half of it growing, that's this part, and the other half contracting, and this minus sign is whether the direction of the payments, the credit or debit. I don't care about that. One is cosh, one is cinch. And I divide by 2 because half of the portfolio is doing this, and the other half is doing that. Okay? Now, that just so happens to have a definition, and we call that the cinch. That's not the interesting part. The interesting part is that this is what it is. And we all know what this is, all right? Well, this is handy, right? And then you can see that the present value of such a portfolio is just this. And you can see there's going to be 2 eigenvalues, right? It picks out this one, and it picks out that one, right? Okay? Sure. All right. Now here is another one. This is the last one. I take that same cinch, and then instead of omega, I put in I times omega. Then it becomes a sine wave, I believe. But this omega d can be imaginary. I don't quite know why I did this. Just think of this. I know why, but it's a discussion I don't want to have. Think of this just as I omega d as omega, right? Okay, just a real number. What I had here is an I times another imaginary number. Now because the damp natural frequency becomes imaginary for damping ratios higher than 1. All right, so All right, so you have here zeta is bigger than 1. And this is what you see. All right. If you just have a regular spring mass system and you would plug in your damp natural frequency, you will see they turn imaginary. I just multiplied by I. Maybe minus I would have been better, otherwise I get a minus sign there. All right, then I get this thing. I'm just giving you a nice little interpretation of why you would have this in a system. So this is a typical overdamped system. So you get this bipoles, but you at the same time, you have a trend that you place on top of it, right? Okay. This is the damping, right? And these are the two conjugate poles. And what you see is this figure. It just kind of like all, and we've had this before. When we had a single pole, we would do multiplied by an e power by shifting it over, and you saw the pole moving on the Riemann sphere. Now the poles move them in pairs, and then you get one over here in the S-plane and one over there, right? This is not quite drawn to scale because this thing comes out way there, and you get a little trouble getting it in a small figure. Now these are very familiar, right? Overdamped systems, they're all like this. Okay? And you see the emergence of the two conjugate poles. So you should know that if you have a second order system and it's not damped, you have two poles here, they just move over, right? And then here it's critically damped, and here you'll see the two, what they call the two real poles. They're not really real, plus we'll find out, okay? They come with the silly cinch here, all right? So, but they're conjugate, right? And the conjugate, see, is just, the drawing is bad, right? They're around some axis here, whatever. Okay? So, what do we have here? We have a situation where we have second order systems, and we see that although they have two poles, which is this quadratic requires, you can't just think of them as two real poles that I can put anywhere, right? It's not like having two first order systems, a pole here and a pole there. Thank you. They come in a conjugate pair that are fixed together, in this way. All right? Okay? And you see they move nicely on the Riemann sphere, to make it all work out. All right. Now, why did I go through this? Because after the break, you'll see this has been a great investment, because as soon as we have real frequencies and we have to start using the Fourier transform, I want to do a little bit more of this. You'll see that then we can really use this extra dimension, and it will all kind of fit together. Why we did all this work defining I as an extra variable, etc. All right? But I want to leave that for after the break. So I'll leave this a little bit here for you to pause and ponder, as some people on the internet say, and then I'll meet you in about 10 minutes, 5:15. All right? Okay, let's keep going. First of all, any questions on this as it stands, right? So we know for complex numbers, we have this extra dimension. I gave a little example of geography, why you would need a plane, but here we have something else. We don't have geography. We have economic systems, but then we have first order systems, and they're kind of in one dimension, and we have second order systems, and they gotta be in another dimension. They gotta have an extra dimension for that extra order, all right? So the parameter space is necessarily higher dimensional, two-dimensional. It follows the, okay? And therefore, the emergence of numbers like I, all right? We're giving the extra dimension. Now the question is, what about when I have two real poles, in an overdamped system, okay? Where is I? Where is there? Why do I don't need that extra dimension? Well, the answer is they're wrong by telling you that you don't. You really do, all right? And only by bringing that in, do you see why this thing is still conjugate and why it's behaving and everything is putting together? All right? So what I want to do now, instead of going straight to the Fourier transform and dealing with the number I, I'm going to talk about this another magic complex number, the number j. All right? And when you square that, you're going to get 1. Now you go to yourself, I'm squaring a number to get 1. Well, think again, because what happens is we're looking at these areas, all right, because we have second order systems. So suppose we want an area of and the area is 1 for some units, 1 hectare. Huh? Huh? And why are the sides 1 and 1, right? It can't be because if this is 1 hectare here and 1 hectare there, then I'll get hectare squared. It's not right. So there's something else there. This must be 1, but then in square root of hectares. Okay? Huh? So it's kind of another dimension altogether. You can't really compare it to the area, right? So if I call this j instead of 1, and I say, well, j squared is 1, then it's a little bit clearer what I'm doing here. I'm calling the sides 3j or 5j, and but there's j, I kind of say, well, it's a side. It's not an area, okay? And then the area I'm calling a nice real number, okay? Huh? Now, suppose I had a square, and I put in the number I. Then I square will be the area, will be -1. Now, what is negative area? You say, well, yeah, it's only because area doesn't really go negative. But if this were charge, right, then you can have negative charge there, no problem. Huh? Or if this were angular momentum or something, there's also area. It could be negative, no problem, right? So then you will see you can use this number I to give the sides, right? And you will need a number j to give the sides when it's positive, right? Huh? Okay? So, well, there's another number which you do when it's 0, but we won't talk about that for now, all right? So just to say that we're really, for a second order system where we're looking at these areas moving around, this is not so crazy. You know, this is really the way we should be thinking of it if we get the units right. I mean, s squared just has different units than s, right? S is in 1 over time, and s squared is 1 over time squared. I mean, huh? Okay. So here there's something funky already. This must have units of frequency, but this whole thing is then, you know, needs to have a 1 or something in here to get the units right, you know? Okay. Okay. To make it a present value. So, let's, with this little writer that this is all not so weird, you know, let's, and actually the right way to go, let's proceed, all right? So now let's just go and look again. Last lecture, I gave this whole thing on these double poles, and I showed you quite a little different one, I believe. You know, it was coming from up and I was going down, and this is a cinch, right? So it's doing this. This is an overdamped system. Okay? Now, overdamped systems are second order systems. And really, they have 2 frequencies, right? So we're going to look at only this one is overdamped. This one is critically damped. And here you see what we will do later. But you'll see that it's this one sometimes is said when it's critically damped that it's exponential, but it's not. How can you see that? Well, in this figure, you can see that look at the derivative at low, you know, at small times here, right? An exponential just takes off like this, right? Or the one of last week would take down like that. But instead, we're seeing this, or, okay? So it's not an exponential. It kind of looks like it, but it's not, and certainly not here, around here. Now, what it turns out, it's 2 exponentials, one going, another one, and they're superimposed. All right? Okay? And the way you can describe this is also through sort of a Fourier transform, but instead of I omega t, I put this number j omega t, with j squared is 1. All right? And then I'm all assuming you guys have recently just looked at 3 Blue 1 Brown's video. There was a good reason, because you see he was wrapping things around the circle. What I want to do is say, well, if this is the same, but then with a J, what are we wrapping around, right? Are we also wrapping around something? And the answer is yes, you're wrapping around the hyperbola, all right? So the hyperbola is like a circle, except instead of the cosine square plus sine square is 1, you have this thing. Huh? Okay, huh? So all this is, you've seen this thing come by a couple of times. So we have also a j-axis. So I made a minus j, so this is minus j. Huh? And I wrap, what I do is I take whatever function I have, and I start trying to wrap this thing around the hyperbola. So you can see the cosh is moving at a particular rate. So first the velocity is very small, it's actually 0 here. And then it starts, converging to this one. Huh? And the sine takes off like a bandit, right? And then starts slowing down to also, okay? And why is this intuitive, right, that we should have this? If you just think of a second order system in the phase plane and you let it go, I mean, here's your momentum or your velocity. Let's put the velocity here. Here's your position. Then at this point, it has no velocity. So what's the damper going to do? It's going to do nothing, right? So if you're not trading, how many costs are you making? Nothing. So at the moment that you're just getting started, this thing is just going to take off like this, right? And then much later, things are messing up and you can't follow your circle, right? So it's just because the damper works on the velocity, or in economics, the depreciation works, of course, the transaction cost, of course, work on the flow of the goods going. If you're not trading anything, you're not going to have any transaction costs, okay? Okay. But you can still take off, without, at 0, because you got this inventory, so you start selling something, but your velocity is very low, your flow is very low, okay? And later on, when your flow picks up, that's how you're going to make transaction costs. That's how brokers get rich, okay? Not on your first trades, but when you start doing real business, okay? So what you can do if you want to imitate 3 Blue 1 Brown, and I kind of don't want to do this, but I want to explain to you that there is sort of a Fourier transform going on for second order systems, is that you're really doing this where j squared is 1, right? It just kind of works out that this looks, because of that squaring, that you got 2 real poles, okay? And then what you do is, if you try to take these functions and you see if they can fit on a hyperbola, it will deviate, some will do this, but you'll find one that fits exactly, and then you got the right one, huh? And you got the right rate here, okay? So I'm not gonna, this is, this I just copied from your book, Khalil's book, where you can see these hyperbolas, right? Yeah? And you can see how the phase flow tries to fit to a hyperbola. These are the asymptotes. Yeah? You can also see that there are these 2 eigenvalues. Only when it's along one of these lines does it stay along the line. Otherwise, it changes. All right? Huh? Okay. Very complicated picture, right? Amazing on the Riemann sphere. It's just 2 conjugate points. Boom. Huh? Why is it two points? Because we have 2 asymptotes, right? One here and one here. And they're conjugate, right? You draw the line, they got to fan out like that. Huh? You can't just keep this one fixed and that one. Huh? Then it won't be hyperbola, right? Okay. This is a very complicated picture. And this is just a couple of points on the Riemann sphere, right? So that's the power of this kind of way of looking at it. And underneath, what you got to see is if you worked it out, and I'm going to leave that to you. is that all you're doing is taking 3 blue, 1 brown things, and instead of wrapping your signals on a circle, you wrap them on hyperbola and see which one fits. Okay? And then you pick out your 2 real poles. And they're built in here. So here, this is the extra dimension. Here it is, the J. Huh? Here's the 2 dimensions. So this is kind of a slide where that's the analog of this slide where I started off with. Remember this slide that you guys all like fell asleep on because you already knew it? So you can make the same kind of slide about these J squared is 1 numbers, right? So instead of a number I plus bi, I have a plus bi, a plus bj. Okay? These numbers are called double numbers, or sometimes hyperbolic numbers, okay? Because you can, the nice thing about them, if this is a double number, then W conjugate is then, right? And then this is a complex number, and z times z conjugate is a squared plus b squared, right? You see these double square numbers, the cool thing about them is you'll get the difference between the areas, and here you get the sums of areas. So very convenient. There I wrote, another cool thing is I wrote this down. Now this is a little bit tongue-in-cheek, okay? But it's a nice little formula because it gives you a bunch of definitions at once, you know? So it tells you in what way the log is the inverse of the exponential function, okay? So this is like e to the I pi is minus 1, right? But the problem is if you're on hyperbola, you're not going to flip to minus 1. But you can move along some kind of hyperbolic sector, you know? And the one thing you can do is not move at all. But the relationship between your movement, the angle, and the boost, the rotation or the evolution is called a boost. And we would call it in economics an expansion, but physicists call this a boost. So it's a space-time boost or something. This kind of math happens in space-time. All right? So with complex number, we call it evolving in economics, or rotation. In regular things, evolve actually means the same thing. But volvare is just a Latin for rolling, okay? A volvo means I roll. Here we would say an expansion, right? So you're expanding. It has the economic idea of an expansion, exponential growth. And this angle, that is that's the growth percentage, right? The logarithm, okay? So you can see that the logarithm takes a boost and gives you the angle, and the exponential map gives you the angle, right? And gives you the boost, right? So the exponential and the logarithmic map is a way to going between angles in regular complex numbers. They go between angles, just like regular circle angles, in rotations, okay? And in these hyperbolic things, these growth things, they go between growth rates or growth percentages and expansions, actually the actual expansion behind it, the exponential growth, okay? So this is exponential growth. This tells you actually that log 1 is 0, right? And you also have an analog of Euler's formula as this one, right? So if you just look at e to the j theta, that's going to be this. And you can easily figure out how to square this stuff, right? You just add the angles, okay? But notice, you see, if you look at this picture and you take an arbitrary point here, then this is here what they call the cosh or the cosine hyperbolic, and this is here the sinh, right? In a circle, you would do this is the cosine, and this is the sine. This is the same thing. All right? Oh, Jesus, yeah. Sorry. The cut and paste was not executed carefully. I replaced I put the H's, but not the J. Thank you. Huh? And this tells you, see, normally this formula is given without the J. The J is left out here, and this is all left out. But why is this bad, right? I mean, it is bad because you just have the dimension. Otherwise, you can't plot the hyperbola. You won't be able to map anything around it, and you'll lose the fact that this stuff is just conjugate, okay? So you got to keep track of that J direction, huh? And you know, Emil gave several very nice presentations about how he sees capital moving with the cosh, and then his interest is moving with the sinh, and together he gets the total growth of the portfolio, all right, or the bank account, all right, when he compounds it. All right? So here you see, I mean, this is all very cute mathematically. But what you got to keep seeing is, my goal here is to introduce this Fourier transform by using some stuff that you already worked with growth and this, and you need to, you know, you can do all the same stuff here, all right? And also you get some, this is a problem. There was a problem for a long time, this log, because people were looking at these problems of quadrature. Let me just give you a little bit of, it started from the Greeks trying to figure out what this length was, you know? So this guy Pythagoras, I'm sure you've heard of him. He wrote down his formula. But what they figured out, what it has to do with comparing areas, right? So this is a squared, b squared, and this is then c squared. And then, you know, these two areas are equal to that, right? Huh? Okay. Now, then they started going like, okay, so we know now what real numbers are. This is really cool. So what we need to do is having a calculus for areas in addition than that for length. So the first problem they faced was, what was the area of a circle? Well, what would you do? You will start putting in a square here, and you add these squares, and you fill it up. But the problem they were having is they wouldn't get there. You know, no matter what, there will be, oh, you can easily see that little pieces left over. You know, so then it took a while for them to figure out how to calculate convergent sequences. You know, the Greeks have put the problem down with Zeno's paradox that some sequences must converge and others must diverge, and then they figured it out, and then they came up with this area to be the number pi, okay? So pi is the area, this is actually 2 pi because, is it 2 pi or 4 pi or something? I don't know. The area of the unit circle is pi, okay? And then this is a unit, huh? That's the definition of pi, by the way, okay? It's not that long thing. This is the definition of pi. So you can't do it by quadrature. You see, you can't square something and then hope to get it. In case of Pythagoras, they could. With triangles, you can. You look at these areas and you square or you add things. But with a circle, it didn't work. So then they were happy for a while. But then another guy says, well, if I can do it for a circle, why not for a hyperbola? I drew the hyperbola a little different way. And the whole question was, what was the area under the hyperbola, say from 1 to when do I get unit area? That was the way they phrased it. Okay? So at what is this point here? Huh? Does anybody know? E, of course. But if you don't have infinite series, you don't know what it is, right? They knew what a hyperbola was, right? And then if you go to say 2, then you know this is log 2 because you just know what the area of you know, when the area is 1, right? Huh? Okay. So that, they knew how to calculate area under a hyperbola, and they had a new function called the log. And it goes with the exponential function. So they come together. Huh? So they were kind of invented at the same time when they were looking at these area problems. All right? And this is why this exponential shows up here. You know, now later, both in economics, where it was invented, but really not, it was invented right here, of course, right? And the problems of quadrature, what's the area under a hyperbola? That's when you know what E is and what the log is, all right? Huh? And then what they did is they defined an angle. So you define an angle to be a piece of area. So in the plane, in this area on the unit circle is then this angle. And in here you would define this angle is the hyperbolic angle. And if you figure it out, it's about the same. It's exactly the same as this area, okay? That's the history of this thing. All right, don't let them tell you otherwise. So what we want to do here is go back to these simple figures and ideas, and then with that, look at economic growth and expansion, and then the e-business cycle, right? And then we go into the way 3 Blue, 1 Brown was visualizing it, all right? You guys are still cool? Good. Let's keep going. So now we're done. So we got a bit of background here. Huh? We took an excursion in the history of mathematics and everything. And now let's go way back to when we first were looking at the exponential function. And remember, it was like a compounding operation, right? So we had this kind of expression. I didn't have the J in there. And I just let, this was your interest, that you would get an interest rate over 1 year over t, and then you would compound it, and then you don't know, and then you would get the exponential function, all right? Now, you can do that now with that j, and you know, you will just get your exponential function. But now I got the little j in there, so I'm being a little bit more subtle about it. Doesn't really matter. The exponential function on the trend is still what it is, but this is to deal with these double poles, okay? Now, really what I want to bring your attention to now is how would this work here with this cyclical thing, okay? So the old one was just doing, you know, now some interest rate, huh? Okay, but now we have this as the interest rate, I times, I should have just put I omega here because S is a complex variable, right? And I mean a real variable, okay? And this is the one, we want to look at systems that are compounding this way, all right? We have been looking at systems that are compounding this way. We want to look at systems that are compounding this way. Now that is a funky thing, right? And somehow we got to get out of that Euler's formula, okay? Now let's just go and do it, and you'll see how easy it all is. So, all right. So this is just continuous compounding, but then with this funky way. Let's just first work it out, and then you can see what's happening. Let's work it out first mathematically. So all I did was write the Taylor series here for the exponential. What is this Taylor series? Well, that's precisely the, you know, the discrete compounding version, right? Nothing exciting. You know, instead of continuous compounding, I'm going to see what discrete compounding amount giving me the same amount of money, all right? Now, it's simple. You just plug in I omega t, then you just work your way through the Taylor series, right? We all know how that looks like. Then all I did here was kind of simplify things because I know that if I make 2 90-degree rotations, I'm going to get to -1, right? So this one will just stay the way it is, but this one is a 90-degree rotation, right? So I first have 1. This is just what I got started here, right? See, this should be a minus sign, and this should be a plus, okay? But it doesn't matter, right? Then the second term takes me down, boink, right? And this is I omega t, right? The third term, I know that I squared is equal to -1, so I bring that out. Huh? And then I'll take, this is here a half plus omega t. You see that? So I go that way, boink. Huh? Because I make here I make a 90-degree rotation because of the I, right? Here I make.
I mean, a second. Right now, the 1/2 omega t squared is the small arrow going up, right?
No, no, no. Listen, 1. Here's 1. Boom. Here's where I got started, right? So t is 0. I'm at 1, right? Then what's the first thing I do? I go in the, and I have a sign error here because later on I realized I want the conjugate because the Fourier transform, and I'd forgotten to put a minus sign here. All right, so bear with me on that one. The next thing I do is I go down I omega t, right? So that's the I-axis. So this is I, right? Then what do? I go, so this is a 90-degree rotation, right? Or minus 90, right? Okay. Then I have to do a minus 180-degree rotation because I have two I's here, right? So there.
That one doesn't have. But there
right.
Minus 1.
Yeah. That one doesn't have a sign error. I'm confused too. So this one, I just did some quick moving around, all right? So had this been flipped, it would all have been fine. So I was doing this. And then later I leave, oh no, I want to go the other way, right? Okay. So with that apology, just, go with me, right? So if you work it all out, this should be that, then this will be that. Yeah, because you got minus I here, and the -1 will just fall out. You see? So it will work. It doesn't have a sign error. You're right. Because that's just the way it works. Because minus 180 degrees is the same as plus 180 degrees. That's why it worked. You see? Because I have, instead of I minus I square that. That's -1 squared, right? Times I squared. So I do 280-degree rotations. Whatever. Just believe me, what happens is the next one is over here, and you'll go until you're here at this point, right? That's the Taylor series for your exponential map. Okay. So if you have a plus, it will go boom, 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 boom. Notice how quickly it converges, actually, how good this thing is, right? Here you would say, what the heck am I doing here? But then you say, whoa, what's going on? So, that's your Taylor series. So you see, you can just eyeball this and you say, well, if I cut it off here, so that's 2 compounding periods, right? And I'm doing okay, 2 compounding periods. That's what treasuries do, normal bonds, 2 compounding periods, pretty close. Okay. And then if you do the kind of stuff Emil does, then you'll see that if you take all the positive all the I terms, you'll get the sign, right? And if you collect all the real terms, you're going to get the cosine. If you collect all the imaginary terms, so those are the odd terms, you'll get the sign, right? That's what Euler's formula is telling you. This is the definition for cosine, and that's the definition for sine. That's what it's telling you. So you know that you have to take the cosine plus I times the sine, of course, because the sine is a real number. All right? So the cosine just tells you how much you got to move on the real axis, and the sine is telling you how much you got to drop or go up. All right? Then we had some discussion about when these things can occur in economics. Now, my first example would be in the phase plane, right? If you have momentum here and position there. Now, what's this guy doing? He has some stock, and he sells his stock, right? Then he's got some credit here, okay? Credit position, and zero stock. But zero, I don't mean that he has nothing. I just mean some kind of desired inventory level. Then he goes short, right? Then he starts dropping his credit level, and that's how he does it. And then I thought to myself, why do that? Let's just go through a more the cows and calves example. You know, now since that's the example we took with Rabobank because they are farmers' bank to deal with that. So, you know, these cows, they can become pregnant and give you calves, but you can think of this as chicken and eggs. It's just a little bit less obvious why it would be a circle. You'll have to rescale it or something, okay? But what you see happening, so this here is some kind of equilibrium expected. This is actually your expected amount of, you know, cows and calves, you know, and I'll call that expectation zero, right? That's all that's happening here, but it doesn't have to be zero. I can have just my expected amount, because you're not sure how it fluctuates around this amount. So if you take the mathematical expectation, right, you'll see that you'll end up here. So these cows, what they do is they just give birth to calves or they die. That's the only two things cows can do. So they don't have, it's not like Minecraft that they have a bunch of lives and all this stuff, right? So here, the first thing that would happen here is that, I mean, when you fill in a circle, of course, you're thinking about half cows dying. But, you know, don't get too stuck on that, right? Just think of it as something you can divide, you know, very finely with seeds or something. I don't care, chicken and eggs. So what happens is one cow dies, and then, but at the same time, in that period, a calf is born, right? Then another cow dies the next period because they're just dying at this rate. You know, you can't, But then you sold this calf, you know, because you wanted to make some money. I don't know how you got rid of it. And then you bought another calf. You made an investment, a cow. So you're now here, and you sold another calf, right, from the proceeds of this thing. I don't know. And then you sold this one. You bought another cow, and but now you get a birth because you had this one. So now your herd is up to date, and this is how it keeps going around. Okay. Now that's reasonable. These models are quite famous. These are called predator-prey models, and I kind of rearrange it a little bit, but they have these fish, like it was figured out also in the 19th century in the Adriatic. They have these fish that eat other fish, and these fish, all of a sudden you have a lot of these prey fish, and they get eaten, so they die. And the other ones are reproducing like maniacs, you know, now because they got all this food, and this is dying, so then they don't have anything to eat anymore, so they will start dying. It's so called right there. Okay. That's just to show you some way in which you can get these circular motions to occur, right? And of course, it has to do with the business cycle. Look at the phase plane. You know, you see that what is a trader doing? He's buying stuff and he's selling it, so then he gets money, and then his money is going up and down, and his stock is going like this, right? When he has to invest, his money goes down, right? His credit amount, and he goes debit on his account, right? He goes debit, credit, you don't know, or the other way around. I don't know. It depends on how you're moving. I think they're moving this way, right? So he's bopping between a credit and a debit balance and whether he's short or long the stock. This is just a very natural movement, right? And you might wonder why he's doing this. There's no point because he's not getting anything out of this. But, you know, maybe he is. Actually, this thing, he could be something getting out of it. Obviously, he's getting more out of selling these calves than he is about than his investment. But who knows? This is here not so important. Okay. But this is the typical thing. This is where the business cycle also comes from, right? So there are two storages. There's the storage of the physical goods, that's the spring, the C element, and then there is the storage of the credit, and that's the mass, right? There you are. And then the two storages are cycling in between, you know? And there's a phase difference between the credit and the thing, and how much of 90 degrees. So you have to multiply this by I to get that, right? So in Euler's formula, if you look at this, and you look at the Fourier transform, you see, you could imagine this is your stock, and this thing is your credit account that you have to set on the y-axis, but you can do it any way you want, right? As long as it all comes out. Okay, but you need a second order system, otherwise you're not going to get this. All right? All right. So with that, and I know you've all watched 3 Blue, 1 Brown's thing. Now, instead of started wrapping this thing around the hyperbola, now we just wrap it around the circle, right? Now, this is not his video, but this is a video of somebody else. So he's got these 3 of these trade cycles or business cycles, and then you want to find out which one is in there. So you start wrapping it around the circle. What does that mean? You take your signal and you multiply it by the circle, right? So this signal is doing something. And the circle, but you can think of this as a circular movement in complex space, which you should, because you have a second order system anyway, right? So you complexify this thing, and then you start matching the wheel that's turning the other way till you get a good fit, right? And then your integral is going to blow up. You have a pole. Huh? That's all that's happening here. So you see, here he's got a huge fit. You know, now you may think, why is this not blowing up? Because he's looking at a Fourier series expansion, and so he's got it all scaled down. This thing is just going to go woo, you know, all the way to infinity on the fit. Okay. All right. So I don't want to talk too much about this because 3 Blue, 1 Brown does a great job. You know. So what I wanted to do here is to see where this wrapping on the circle comes from. And how you should see that is in extracting the business cycle. And it's a bit of a story. First, you have to see that we're dealing with second order systems. So they're in 2 dimensions, okay? Then you have to see that the compounding in this 2 dimension just goes in a little weirder way. It's the same thing, but instead of all plus signs here, you get these alternating minus and plus sign because you keep turning, okay? So if you have cows, they give you calves. They don't just give you more cows, you know, which you would have if you have a trend, okay? You have the extra dimension. If you have a stock, you can sell it for money. You don't just get more, and then with that money, you could buy new stock. But that's a different operation. You first have to sell it in order to buy more. You know, that's what a second order economic system is telling you, okay? That's what you got to see. Huh? If you only have a mass and a damper, all you have to have some demand and a bunch of transaction costs. You don't, you know, you're just selling it, whatever, right? Huh? But you're not stocking up, right? You're just kind of going, and all that can happen to you is that you slow down or you speed up in the direction you're going, right? But you're not going orthogonal, right? And we plotted it orthogonal, you know. And it has a meaning because you can say, well, this angle makes no sense, but then I squared would not be minus 1, you see? So it does have a meaning. It's got to be 90 degrees, all right? That's the way we set it up. So we have a cow dying in the same kind of time cycle that it took to get a birth, okay? And these things are going like that, and these are like that, and they have a phase difference of 90 degrees here. If there was phase difference was different, then this circle, this ellipse, would it be squeezed to another ellipse? And I don't know. Huh? Okay. So I got 5 minutes, and I want to wrap up. Huh? So now we have a situation where we're wrapping on this circle, but we also have the other circle where we could do the trend. Okay, when we look at first order system. So we really have 2 circles now, okay? So here I made a picture, and I don't know why I got the perspective wrong on this thing, right? Huh? It's irritating, huh? And of course I know, because the person I stole it from got it wrong. So here's a picture of the S-plane, the complex plane, and I've decomposed it now in sigma and omega. So what you have to see is that now S is sigma plus I omega. So this is really I omega. So here's the I-axis, and this thing here this is the real axis, right? Now, the one that we were always looking at was this one, right? So we were looking at our real poles and everything. But now we got that other circle of cows and calves and all this stuff, right? So we have to add another circle that is this circle right here, okay? So I have a circle on the equator, and I have a circle in the meridian, say the Greenwich meridian. I don't care, right? So this is my sphere now, all right? Now I can look at any combination. So I can take either the equator circle and just kind of rotate it around like that, or the meridian and just buzz it around along this circle, right? Okay? Either way, I'm going to get a sphere. And this is the North Pole. So I'm going to get the whole complex plane. So this is the complex plane. And there's going to be one point at infinity, and it all gets mapped to the North Pole, right? So these ones get mapped to the North Pole, but those ones too. Okay? All right? And the bottom hemisphere, which is the southern hemisphere, gets mapped to go into the circle. The top goes out, and I got the whole S-plane. All right? Now, I just want to leave this here like this, because this is what we're going to do in next lecture. We're going to look at this and analyze it, etc. Because now we're in business, right? We have these two ways of looking at it, you know, along the real axis, along this imaginary axis. We have a way to look at conjugacy. So we're going to get conjugacy we've seen before, but we can now also see it in the other direction, where you see along a meridian, you know, that is 90 degrees on the Greenwich meridian. You're also going to define a notion of conjugacy. That's for underdamped systems, right? And then everything will become this one theory where we can use a Laplace transform to analyze systems that both have trending behavior and second order effects, whether they are, you know, cyclical, or whether they are, you know, these kind of hyperbolic ones, you know, temporal one. In the beginning, the stuff is just more worth than at the end, you know? These are hyperbolic things. And we can have two types of Bode plots and two types of everything, okay? The beauty of the Laplace transform is just puts it all together. If you go to economists and say, hey, I got complex discount rates, you know, then it just goes, okay, I can't believe that. You know, what's the meaning of that? But you know. In fact, if you go to a controls guy and you say, listen, I got discounting rates that are real, he kind of goes, oh, wow, never thought of frequency. I always thought it was a real frequency. I didn't know it was a discount rate. Economist is going to be the opposite. You can put both together. And the Laplace transform gives you that one solution where you can look at any problem, and it's just this Laplace transform, and it is what it is. Okay? You don't need anything more. Okay? The solution is closed. There are no further things than cycles and trends. Okay? So with this, I reach my time, and I want to bid you all farewell until next week, where we're really going to explore this Riemann sphere, and then hopefully, you know, fill this section on valuation. Okay? Until then, see you guys Thursday for our colloquium.